What we're here today to do is to do a factory acceptance test for the Vrcm equipment. It's going to be an integral part of a total demilitarization process for problematic munitions at the Bluegrass Chemical Army Depot. In particular, we have a group of rockets that present unique challenges in processing and destroying the chemical agent. And Crown and CRG, Dynasafe, Amentum have partnered together to provide the government with some really elegant solutions to handle difficult engineering problems.
The Vrcm system is a much more elegant system than what I'm used to. I've been around and I've seen the other RHS systems systemize this. This is a much simpler way to handle the situation we have, a good solution to the problem that we have.
The biggest impact on this project, I believe, is moving the orientation of the cut from a horizontal cut on the original design and application to a vertical cut. This keeps all the nerve agent contained in the event of a process reject and is a lot safer for the end user as well as the operators.
In an effort to provide context to the vertical rocket cutting machine, or VRCM, we will start this video with a high-level view of the M55 rocket line at BGCAP. The M55 rocket lines consist of 4 primary processing rooms: the unpack area, explosive containment vestibules, explosive containment rooms, and the energetics batch hydrolyzer room. The VRCM processing will take place in the explosive containment vestibules, ECV1 and ECV2. The primary function of the VRCM system is to safely separate the outer shipping and firing tube and the M56 warhead from the lower M67 rocket motor assembly and shipping and firing tube, so that the warheads can be processed in the downstream rocket warhead containerization system. From the unpack area, M55 rocket assemblies are conveyed into the ECVs on line 1 or line 2. In the ECVs, the upper half of the shipping and firing tube is cut and removed, exposing the M56 warhead, which is then cut and removed from the M67 rocket motor. Once separated, the M56 warhead is transferred and conveyed into the respective ECR, and the M67 rocket motor is transferred and conveyed into an adjacent motor pack room not shown in this illustration. Additionally, the VRCM system has several automated reject modes that allow the control room operators to process problematic munitions, which we will show you later in this video. The VRCM is a custom engineered processing system that is made up of 3 primary elements. First is the automated production process. Second is the vertical rocket cutting machines. And finally, the process reject stations. This system was designed and built through a collaborative effort to produce a safe and efficient processing environment. The VRCM systems in ECV1 and ECV2 are identical and mirrored processing rooms. Each room consists of the following equipment: an input conveyor, 2 VRCM machines, one is for redundancy or backup, 1 VRCM robot, a process reject station, a single reject rack, a transfer station, 1 transfer robot, and output conveyors. The VRCM system is integrated into the BGCAP control system, or FCS, which controls the overall flow of inbound and outbound munitions through the process. Now let's take a closer look at the primary equipment in the VRCM system, the vertical rocket cutting machine, or VRCM, and the process reject station, or PRS. The vertical rocket cutting machine incorporates a high-speed 2D optical micrometer for measuring the cut length of the M56 warhead by using the tip of the fuse end as the reference point, with an accuracy down to 1/1000th of an inch. The optical micrometers are also programmed for detecting fault conditions during the rocket processing. The VRCM cutting assembly consists of 2 smart electro-hydraulic actuators, or SHAs, that provide linear force to the cutter assembly and the back roller assembly during the cutting process. The SHAs are capable of precise force and distance control with continuous feedback provided to the control system. The VRCM cutting table's rotary motion is accomplished with a servo-driven precision reduction gear that controls speed and torque to the cutting assembly. The cutter assembly rotates approximately 370 degrees, alternating back and forward bidirectionally around the statically held SFT. The first full rotation will measure any eccentricity that may be present. The eccentricity is then incorporated into the following rotating cut process using an appropriate speed and force to address out of round or warp conditions that may cause cutting issues. The underside of the VRCM cut table incorporates a set of lower clamps for securely holding the SFT during cutting operations, a lower SFT lift mechanism that will raise and lower the SFT assembly to the prescribed height, and a removable containment bucket that is intended to capture any liquid agent that may flow out from a process reject. The process reject station was designed to allow for the automated processing of rejects that have been found to contain leaking liquid agent. As these munitions have been stored for over 60 years, it is possible to encounter these inconsistent units, and therefore the system has been designed to safely contain the problematic munitions and limit the amount of chemical liquid or vapor exposure in the ECVs until a demel protective equipment or DPE entrance can be made into the room to manually complete the overpack and removal operation. A single round container, or SRC, is the primary overpack container for a M55 process reject. Operators will first prepare the SRC in the unpack area by removing the SRC flange and bolts and placing them in a plastic bag labeled with the SRC serial number. Then the operators will insert an upper half SFT into the SRC and finally place the entire SRC assembly into an overpacked plastic bag to keep it clean. When the SRC preparations are complete, the operators will load the SRC assembly onto the process reject station and secure it in place with clamps. During the VRCM process, a rejected unit is robotically placed on the process reject sled. The sled contains a rear pusher with a replaceable butyl seal that, once activated, will pneumatically push the rejected units into the SRC and provide a rubber seal against the SRC flange to reduce or eliminate agent vapors in the room until a DPE entry can be made to manually apply the end cap and remove the SRC. The process reject station has been designed with pivoting action to further control and contain the spread of liquid agent during the reject process. When the process reject is first loaded on the sled, the pivoting table will be in the up position. Once the process reject has been loaded into the SRC, the pivoting table will transition to the down position, utilizing gravity to keep the agent contained in the upper half of the SRC until a DPE entry can be made. We started the factory acceptance test in an automated single-line processing mode, utilizing line 2 and VRCM table 2A. 5 simulated M55 rockets were successfully processed during this demonstration. Here we see the first SFT entering ECV2 on the input conveyor. Once the SFT reaches the end of the input conveyor, the VRCM robot will pick and place it into the VRCM table, and the lower clamps will be engaged. The VRCM rotating cutter assembly will now slowly begin its first rotation, allowing the SHAs to precisely record approximately 120 linear measurements that will detail any eccentricity present in the part. Upon completion of the first measurement rotation, the VRCM will fully engage the cutter and back roller assemblies, and the first cutting process will begin with the cutter assembly rotating approximately 370 degrees, alternating back and forward bidirectionally around the statically held SFT. It should be noted that the robot end of arm tool is not clamped on the upper SFT during this first cut. This allows the VRCM table to efficiently process the first cut on the SFT if the part has any warpage or bowing present. Once the first cut is complete, the VRCM robot will provide a quarter turn twist and lift motion to the upper SFT. This twisting motion ensures the internal scale or debris that may have built up over the years is broken free prior to removal of the SFT. The process will then pause and wait for the control room operator, utilizing their CCTV feed, to review the first cut. The HMI will provide the operator with 3 processing options: accept, reject, or retry. When accepted, the VRCM robot will remove the upper half SFT and place it on the transfer station. Next, the 2D optical micrometer will take a measurement of the M56 warhead fuse tip and provide input to the SFT lift mechanism that will then disengage the lower clamps and lower the SFT assembly to the desired second cut height. Once the proper height has been set, the lower clamps will re-engage and the robot's end-of-arm tool will securely clamp the M56 warhead. The second cut process will now begin. At the completion of the second cut on the M56 warhead, the robot will again raise the warhead approximately 4 inches to allow the control room operator to inspect the cut and then accept, reject, or retry. Upon acceptance of the cut, the transfer robot will pick up the upper SFT from the transfer station to begin conveying it out to the motor pack room, while the VRCM robot will remove the warhead and place it on the transfer station, and the VRCM table will disengage the lower clamps and eject the lower half SFT and rocket motor. The transfer robot will pick up the warhead from the transfer station and move it to the output conveyor that will transport the warhead to the start of the RWCS system in the respective ECR. The VRCM robot will subsequently pick the lower half SFT and rocket motor and move it to the transfer station. Finally, the transfer robot will move the lower SFT and rocket motor to the output conveyor that will convey the unit from ECB1 to ECB2, where the transfer robot in ECB2 will be commanded to transfer the part to the final output conveyor that leads to the motor pack room. The next part of the factory acceptance test demonstrates automated dual-line processing mode utilizing line 1 and line 2 in VRCM tables 1B and 2B. A total of 10 simulated M55 rockets were successfully processed during this demonstration.
On my mark. Mark. All right, group, for this run, we did dual line processing. We ran 5 rockets on both lines. My time was 23 minutes, 23 seconds was the total time that I recorded. If you notice that on line 2, there was a stoppage on it at rocket 4. Rocket 4, the tolerance for the measuring of the warhead into the fuse is 2 millimeters. That's the tolerance. It was 2.1 millimeters. It was too high, so it got a stop command. Part of the programming. The control room operators had to go in, accept it to allow it to continue processing. All things that we were going to see during processing. We've had the examples of the double cut on shipping firing tubes. We had examples of second cut and even a third cut on the warhead. All those are going to be noted in the report, but I did want to note that to this group for what we're doing here.
The VRCM system has been designed to automatically process various potential reject modes. The first 2 modes are process rejects due to liquid agent leakage, and both utilize the process reject station. The first type of reject would be found during the first cut of the SFT, whereby liquid agent would have leaked from the warhead into the SFT spaces. The second type of reject would be found during the second cut of the M56 warhead, whereby liquid agent would have leaked from the warhead into the interstitial space between the warhead and the rocket motor's foreclosure. It should be noted here, a Rocket Non-Destructive Examination System, or RNDE, is being installed in the unpack area to minimize the likelihood of liquid agent being detected during cutting operations in the ECV. The third reject mode occurs when the fuse cushion becomes adhered to the fuse. This failure mode, if left uncorrected, would present downstream processing issues during the containerization of the warhead. The last two failure modes do not result in any specific reject action taking place, but rather the VRCM system has been designed to automatically accommodate and process the non-standard conditions of a warped, bowed, or out-of-round M55 rocket assembly. As previously described, the SRCs will be prepared in the unpack area prior to placing them on the process reject station. As part of the preparation, a small piece of adhesive-backed foam tape is placed on the upper half SFT across the centering ring. This foam tape provides additional friction to the upper half SFT that will prevent it from prematurely sliding during the reject process. Here we see the prepared SRC placed on the process reject station and is ready for operation. An upper half SFT can be seen inside the bagged SRC, and the SRC clamps have been engaged. The last step in preparing the process reject station is to replace the butyl rubber gasket on the rear pusher. That's it. So we got both lines loaded now. These particular rejects have been loaded with concrete to simulate the actual weight of a full rocket and a warhead.
Automatic mode right now. Reject 2B.
At this point in the process, the control room operator has identified a potential leaker and will select the reject command in the HMI to carry out the automated process. The first step in the process will raise the reject station to the up position to prepare for loading the process reject. The next step in the process, the VRCM robot will remove the potentially contaminated upper half SFT and place it upside down, or open side up, into the single reject rack.
Upside down, cut end up for AD containment purposes.
The VRCM table will then disengage the lower clamps holding the SFT and eject the remaining M55 assembly so that the VRCM robot can remove it and place it on the process reject sled. Once the entire M55 has been loaded on the process reject sled, the pneumatic cylinders will engage and drive the rear pusher and sled into the SRC. At the completion of the reject process, the rear pusher butyl seal will be pressed against the SRC flange to create a seal, and the process reject station will then pivot into its down position. At this point, a DPE entry will be required to manually install the end cap and unload the SRC and complete the overpacking process for its final removal from the room. At the completion of the SRC removal, operators will have prepared the next SRC in the unpack area and may begin resetting the process reject station prior to restarting the automated VRCM process. The next failure mode demonstration occurs after the second cut, or warhead cut. In this scenario, the control room operator would have accepted the first cut of the upper SFT, and the VRCM robot would place the clean upper SFT onto the transfer station. It is important to note that the VRCM process does not allow the upper SFT to be transferred downstream until the second cut has been completed and confirmed. The control room operator now identifies potential liquid from the second cut of the warhead and selects reject on the HMI to begin the reject process. Again, The first step in this process is to raise the process reject station to its up position to prepare for loading. Once the station is ready, the VRCM robot will place the warhead onto the reject sled in the appropriate position. Next, the VRCM will disengage the lower clamps and eject the lower SFT and rocket motor so that the robot can pick and place the potentially contaminated parts onto the reject sled. Once the reject sled is loaded, the VRCM robot will remove the upper SFT from the transfer station and place it upside down in the single reject rack. As this is taking place, the reject station will engage the pneumatic rear pusher and sled and drive the M55 rocket assembly into the waiting SRC. Again, when the entire M55 rocket assembly has been inserted and sealed into the SRC, the reject table will pivot into its down position and is now ready for a DPE entry. The next failure mode demonstration occurs after the control room operator has accepted the first SFT cut. As you can see here, once the upper SFT is removed, the rubber fuse cushion from the end cap can be seen stuck to the fuse of the warhead. In this case, the 2D optical micrometer is programmed to check for this failure mode automatically. When the cushion is present, the HMI will alert the control room operator to the defect mode, and the control room operator will be asked to confirm prior to initiating the reject mode process. The reject mode process will begin by transferring the upper SFT to the transfer station per standard operations. Once the upper SFT has been placed on the transfer station, the VRCM robot will return to the VRCM table and will rotate its end of arm tool 180 degrees in order to utilize the specially designed cushion removal gripper. The stuck rubber fuse cushion will be robotically removed from the warhead and will be transferred over to a cushion reject container that is attached to the transfer station. At the cushion reject container, a sensor is used to detect successful placement of the cushion into the container, and the control room operator is notified in the HMI. Once the fuse cushion has been successfully placed into the container, the VRCM processing will continue per standard operations. It has been observed at BGCAP that some of the M55 rocket assemblies could contain physical deformations such as bowing, warpage, or outer roundness due to the prolonged storage conditions. Here you can see a mated warhead and rocket motor on a flat table showing an induced warpage of approximately 1/4 inch. We have intentionally induced this deformation to demonstrate how the VRCM is capable of processing this type of defect without operator intervention. Here we see the VRCM beginning the second cut process on the previously shown warped assembly. As you can see, or not see in this case, there is no visible difference in the cutting process of a normal or deformed assembly. The VRCM will continue cutting the warhead per standard operations, and the result is a successfully separated warhead. Upon closer inspection, the resultant cut on the deformed warhead showed similar separation patterns as the previous normal cut assemblies.
The FAT today went really well. We're real pleased with how the system's performed. The cuts have done exactly as we expected. We built in recuts in the event that there's issues with the initial cuts, so that way we can keep processing. We minimize operator entry as well as minimize agent contamination.
So just how well the equipment has ran, how the solution to the problems, one of them being the overpack. I love the ability that we can overpack a leaker without having someone being exposed. So it's a much better way to handle those kind of situations.
I would have to say it's less about the equipment and more about the collaboration between the different entities. Working with Crown and CRG and Amentum and Dynasafe and even the JV with Bechtel and Parsons, the teamwork of that to get to this point is impressive. And that, I think, has led to the quality of the project. We're going to all provide the customer a great product in the end, because we've been able to provide clear and concise direction. Ken has done a really good job in leading us in that way, but I think it's a whole team concept to get to such an elegant solution.